Hello all, welcome to Sri Vishnu Engineering College for Women. We have done a course activity under the guidance of Dr. M. Prasad, PhD, Associate Professor in the Department of CSC from Bhimavaram. And my name is Samatha, my roll number is 51 and my partner name is Satvika, her roll number is 11. And our topic is memory management and swapping. In memory management, mainly there are two parts: contiguous memory allocation and non-contiguous memory allocation. Now coming to the contiguous memory allocation, it is divided into two parts: single partition and multiple partition. Multiple partition again divided into two parts: fixed and dynamic. Fixed means multi-program fixed task memory allocation. Dynamic means multi-programmed variable task memory allocation method. And again fixed is divided into two parts: equal sized and unequal sized. Coming to the non-contiguous memory allocation, it is divided into two parts, that is paging and segmentation. Introduction to memory management. Memory management is an essential aspect of computer systems. It involves the allocation and deallocation of memory resources. Effective memory management ensures efficient utilization of the available memory. Now coming to the types of memory. Primary memory and secondary memory are the two types. Primary memory, also known as RAM, is directly accessible by the control processing unit, that is CPU. And secondary memory such as hard disks, drives is used for long-term storage. And there is an extension, that is virtual memory. It is of primary memory and secondary memory as a backing store. Now coming to the memory allocation techniques, that is contiguous memory allocation and non-contiguous memory allocation. Contiguous memory allocation is also called as static allocation, and non-contiguous memory allocation is also called as dynamic memory allocation. Coming to the static allocation means static allocations assigns fixed memory blocks to process at compile time. Dynamic allocation allows memory to be allocated and deallocated only during the runtime. Partition allocation divides memory into fixed partitions for different processes, and it also divides into variable size partitions for different processes in non-contiguous memory allocation. In contiguous memory allocation, each process gets a contiguous block of memory, making it easier to manage, but potentially leading to the fragmentation issues. This is the drawback of contiguous memory allocation. To overcome this drawback, non-contiguous memory allocation is introduced. This allows for more flexible memory utilization but requires additional data structures to manage the different parts of each process. Now coming to the paging. In paging there are mainly three statements. That is, if a process is stored in logical memory, then each partition is called as page. All the partitions, that is page size, should be in equal size. The page size is decided by the operating system. Now physical memory is divided into partitions, that each partition is called as frame. The size of page should be equal to the size of the frame. So pages are inserted into frames, and paging allows for efficient memory allocation and helps avoid external fragmentation. Now, by seeing the diagram, we can understand the logical address has two parts, that is pages and displacement. The pages are connected to the page table, and that page table provides the frames. And another part in physical address, that is displacement. The both displacements in logical address and physical address are connected, and those all help to physical memory to show the where the pages are saved. This is about the diagram. And there is also an drawback in the paging, that is risk of fragmentation, particularly external fragmentation, where free memory is scattered in small blocks but is not contiguous. This fragmentation can make it challenging to allocate contiguous blocks of memory for larger processes. Paging may also be lead to increased input or output operations as pages need to be swapped between the random memory allocation and secondary storage. This can impact system performance, especially when dealing with heavy disk like operating systems. While paging helps in optimizing memory usage, it's essential to balance its advantages with these potential drawbacks and consider system specific requirements for efficient memory management. Now coming to the segmentation. Segmentation is another memory management technique used in operating systems. Unlike paging, which divides memory into fixed sized blocks, that is pages, segmentation divides memory into variable sized segments based on logical grouping of information. Each segment represents a different type of data or module within a program. The key aspects of segmentation include logical organization, addressing, flexibility, fragmentation, protection, and dynamic memory allocation. Coming to the discussing of logical organization. Segments are defined based on the logical structure of a program, such as code, data, stack, etc. Each segment has a specific purpose and can vary in size. Addressing. Instead of using a single dimensional address space, segmentation uses two-dimensional addresses. A segment identifier and an offset within the segment are used to address memory. Flexibility. Segmentation allows for a more flexible memory allocation as different segments can grow or shrink independently. This flexibility is beneficial for supporting data structures of varying sizes. Coming to the fragmentation. Similar to paging, segmentation can also suffer from fragmentation, both internal, that is, unused space within a segment, and external, unused space between segments. Protection. Segmentation provides a natural way to implement protection as access permissions can be assigned at the segment level. It helps in preventing unauthorized access to specific parts of a program. Finally, dynamic memory allocation. Segmentation facilitates dynamic memory allocation as segments can be allocated and deallocated independently, while segmentation offers advantages in terms of local organization and flexibility. It shares some drawbacks with paging, such as the potential for fragmentation. In some systems, a combination of both paging and segmentation, known as segmented paging, is used to leverage the benefits of both approaches. Now let us discuss about the second part of our course activity, that is swapping. So swapping is a memory management technique used by operating systems to temporarily move data from RAM to disk and vice versa. This is done when the physical RAM is full and the system needs to free up space for other. This swapping process allows the operating system to effectively utilize limited physical memory by storing temporarily unused data on disk. However, swapping comes with a performance cost since accessing data from storage is slower than accessing it from the RAM. Excessive swapping can lead to decrease in system performance known as thrashing as the system spends more time moving data between RAM and the storage than actually performing useful tasks. Swapping is mainly useful in order to implement multi-programming system. The concept of swapping has divided into two concepts, swap in and swap out. Through multi-programming, CPU can be utilized in efficient manner. CPU can access only main memory. That is the reason why a program executes if and only if it resides in main memory. In main memory, space is allocated for both OS and the user program. This is the diagrammatic representation of swapping. Let us assume that process 1 has completed its execution
Then process 1 will transfer to the secondary memory. This transfer is known as swap out, and the process of transfer from secondary memory to the main memory is known as swap. Let us discuss about some main cases of swap out. When a process finishes all its operations, and when a process finishes CPU operations and waiting for IO operations, during the time protection violence, OS generates interrupt or trap, so process will be terminated forcibly. During the round robin algorithm, we execute a process for particular time quantum. If that time completed, then swap out happens automatically. And during the priority scheduling algorithm, if a high priority comes into the secondary memory, waiting for its task to complete, and during that time OS swap out low priority process and swap in high priority process to the main memory. Now let us discuss about the advantages of swapping. Swapping in OS helps in achieving the goal of maximum CPU utilization. Swapping ensures proper memory availability for every process that needs to be executed. CPU can perform various tasks simultaneously with the help of swapping, so that process do not have to wait much longer before execution. Swapping ensures proper RAM, main memory utilization. So there are also some disadvantages of swapping. Let us discuss about the disadvantages of swapping. So firstly, if the system deals with the power cut during the bulky swapping activity, then the user may lose all the information which is related to the program, which means that the information may be lost. And secondly, if the swapping method uses an algorithm that is not up to the mark, then the number of page faults can be increased, and therefore this increases the complete performance. Here comes the end of our topic. Thank you. This is presented by Satvika and Samata from Cybersecurity.